It's somewhat interesting to look and see what's happening inside a conductor as it's carrying electricity. And it's actually surprising what we find. If we think about a wire carrying current, okay, we imagine in this particular case, we have positive charges carrying it, but of course we know that electrons carry it in a metal. But think about this. We have charges carrying. We're going to use the positive charges, then reverse it for negative charges. In a particular volume, the volume that is enclosed is going to be equal to some distance delta x, where that delta x is actually going to be the average drift velocity. What I mean by drift is how quickly the charges move. They're moving very randomly, but if I average out their motion, how they're going to move in meters per second from left to right in this diagram, times delta t, the time that this is measured over. So when we're looking at velocity, velocity is distance divided by time. Nothing's really changed here. We're really trying to analyze how these charge carriers are moving in terms of what their average velocity is. Now, if we look at the total number of carriers that are in this volume, this cylindrical volume of this wire, we see that the number of charge carriers is going to be equal to this small n. That is the carrier density, the number of electrons per meter cubed. A is a cross-sectional area of the wire. So if you have a cylindrical wire, of course, most wires are cylindrical the way that they're drawn out. That area is going to be pi r squared, where r is the radius of the wire. Delta x, again, represents the length along this wire. And obviously Q is the charge per carrier, which if we're dealing with electrons, that would be the elementary charge. So let's look at the drift speed first of all. Drift speed again is defined as delta x divided by delta t. How long of this section of wire we're looking at divided by the time that these carriers move along that section. We can now rewrite our total charge as being dependent on this equation. What we've done is we've replaced delta x with the basically velocity times the change in time. Of course, x is measured in meters. If we take meters per second and multiply that by seconds, we get back meters. Again, Q is our charge. And finally, we plug this into our current equation, delta Q over delta T. This delta T will cancel out with this delta T, and we're left with the current being equal to the number of charge carriers times the charge per carrier, the drift velocity, and the cross-sectional area of the wire. Okay, now, if we consider silver, excellent conductor of electricity, it's an excellent conductor because actually it has a very high number of carriers, has a high carrier density. We look at a wire with a cross-sectional area of 6.3 times 10 to the minus 6 meters squared. So roughly, we're looking at a wire that's fairly thin, a little over a millimeter across. Let's say it's carrying a very large current for that size of wire of 1 amp. What is the average drift velocity of the electrons, assuming in this metal that we have 5.8 times 10 to the 28 conduction electrons per meter cubed? Now remember, we can come up with this type of estimation if we look at how many charge carriers we get per atom, okay? How many atoms are in a cubic meter? Thinking about 1 mole of material, it doesn't take much to get a very, very large number. And of course, this is a fairly high carrier density, but again, when you imagine a cubic meter of silver, you would have a very high expectation for the actual number of atoms there and the number of charge carriers. So back to our equation right here, we have our current, number of charge carriers per volume, that's our N. Q is going to be equal to the elementary charge. We're looking for the drift velocity on average, how fast are these moving, and then again, the cross-sectional area. Now, instead of solving for I, because we have I already, it's 1 amp, we're going to solve for the drift velocity. We get this equation right here. Drift velocity is equal to the current divided by the charge carrier density divided by the number of coulombs per charge in the cross-sectional area. So in the denominator, we have a very large number times a relatively small number times another small number. This is still an overwhelming number right here. And when we put everything together, we get an incredibly small drift velocity of 5.8 times 10 to the minus 6 meters per second. Okay? Let's put this in perspective. This means that it's moving at 5.8 microns per second. Okay? If you watch it under a microscope, obviously electrons are too small to see under a microscope. You know, cells can move at that speed. If you've got like one cell, you know, protozoa, move at that sort of speed. So we got really small velocities for these electrons moving, but that doesn't mean that they're not moving very quickly within the metal. Really, think about the electrons as almost being in a gas-like state. Obviously, they're bound within the metal itself, but they're moving due to their thermal energy. So they're moving all in random directions. Now, that doesn't mean that just because we've heated up a conductor, a metal, that we have electricity flowing. We have an equal number of electrons going to the left as we do going to the right without current flowing. So the movement of charge cancels out. It is the net average when we take into all the motion of these electrons that produces a current. So again, on average, you can actually do a equation. You can actually come up with an equation for the root mean squared velocity based on temperature and their mass. You come up with a really high velocity. You know, I can't do that off the top of my head, but we're talking about thousands of meters per second. These things are bouncing all over the place. However, on average, their net average speed is this way. It's very analogous again to the air in this room. Right now, I don't have any wind blowing through this room, but on average, the speed of the molecules is pretty close to 300 to 400 meters per second. Okay? But the wind speed, if I were to open up a window, might only be a few meters per second. It doesn't mean the molecules aren't moving. It just means that their net motion isn't necessarily in one direction. So the electrons, the average, statistical average, what they're doing is they're moving from left to right on the order of 10 to the minus 6 meters per second. Okay? What is their overall speed on average, or their mean speed? Much, much higher than that, into the thousands, 10s to the 4, 10 to the 5 meters per second, much, much higher. And again, this is an underrepresentation in terms of the randomness of the motion. The randomness of this electron moving from left to right as it's carrying current would be even greater. This is just sort of a representation that most of the motion is random, but the electron eventually makes it from one location to another. Okay? So, again, what the electrons are doing and charge carriers are doing within their conductors is most of the motion is just due to thermal energy. Okay? And, of course, the motion becomes greater as their mass drops off. Again, we saw that from previous chapters. It is just the net motion when everything cancels out. The electrons going to the left, the electrons going to the right, up, down. When we take the net effect of all of that together, then we get this slow motion. All right. With that in mind, let's do a little thought experiment right here. If I turn on the switch, why do the lights go on instantaneously? I know with some LED lights we actually get a lag. With some incandescent lights there's actually a perceptible lag too sometimes. But really, I turn on the switch, the object is on, the appliance is on, the light is on instantly. Okay? It's not that the electrons located at the switch begin traveling to their destination. All right? In fact, if I'm at home, I'm using alternating current. It's moving back and forth. So we look at that 10 to the minus 6 meters per second, it's actually oscillating back and forth in place. The electrons in the switch really don't get to go very far from their location. What's important to understand is the wire is not just carrying current with it. The wire is carrying an electric field. And I switch this on, it's the electric field that is transported to whatever appliance that I'm using. So that's very, very important to understand that the actual drift velocity of the charge carriers can be very, very low, but the electric field moves at the speed of light. So when we send an electrical signal, when we send electricity, that is propagating pretty much at the speed of light within that wire. Okay? So again, drift speed is much smaller than the average speed between collisions of these electrons. But again, when the circuit is completed, when we turn that switch on, we are allowing the electric field to propagate through our wiring system, and therefore that allows the device to go on almost instantaneously. Drift speeds, in very good conductors, 10 to the minus 6 meters per second. Not as good conductors, maybe 10 to the minus 4 meters per second. But it is really the speed of light, which is on the order of 10 to the 8 meters per second. In a vacuum, it's 3 times 10 to the 8 meters per second. That is propagating this electricity. Okay? So again, don't just think of electricity as the charge is flowing from one point to another. Think of the electricity as the charges moving within an electric field, and because they move, they carry energy with them. Last point, sometimes you'll see this, not as important for a lot of what we discuss. We'll talk more about this when we talk about conductivity and resistivity. But especially in higher level electrical, analog electric courses, you'll sometimes come across this quantity called current density. Current density is the amount of current that we have passing through an area. Technically, current density is a vector, okay? Current will give it a positive or a negative. It's technically a scalar. But the current density technically is a vector, and it'll point in the same direction as the electric field. It represents how much current we have passing through a particular set amount of area. And when we look at this area, that area A usually represents the cross-sectional area of a wire or other type of conductor. Okay.